Human beings have known of electrical phenomena for thousands of years. Yet when we speak about electricity today, the meaning is much more complex. In this video, we will learn more about the way today's electricity is generated and delivered. We'll also look at the growing need for electricity, the challenges this poses for the electrical grid, and how these challenges are being addressed.
Electricity is still generated using the principles developed by Michael Faraday in the 1820s and 1830s. Copper wire wrapped around a shaft or armature is spun in a magnetic field. The motion of the magnetic field relative to the copper wire causes electrons to flow in the wire, creating electricity. It takes a source, such as a battery or a generator, to put electricity into a circuit, and there it flows at almost the speed of light. Before it reaches our homes and offices, electricity is transmitted from the power plants at 300,000 kilometers per second along the network of transmission and distribution lines that we call the grid, which is monitored and controlled in real time. While transported, part of the energy is lost due to current resistance in the lines. One way to reduce losses is to step up the electricity generated by power plants to higher voltages using a transformer. Depending on the country and distance of transmission, voltage levels range from approximately 52,000 to 250,000 volts and will soon reach as high as 1,200,000 volts on transmission lines. Closer to cities, where distances of lines are shorter, the distribution grid operates at lower voltage levels, usually below 52,000 volts. The electricity supplied to us through the grid is transmitted as either alternating current, AC, or as direct current, DC. Why do we have two types of current?
Thomas Edison's company was producing electricity in 121 power stations by 1887 using the DC system. One advantage of DC is that the voltage, the electrical force needed to drive current between 2 points, is fixed. This is useful for applications that need an unvarying supply, such as electric railways. However, Edison's DC system could only supply customers within about 2.5 kilometers of the plant. Thomas Edison's great rival was George Westinghouse and his AC system. With AC, Westinghouse was capable of transmitting current over hundreds of kilometers and soon won the war of currents. That is why today, AC remains the standard for electric power. Here is an example of today's electrical grid. Let me show you how the power flows. Electricity is generated by different types of power plants, such as nuclear, gas, coal, wind, offshore and onshore, hydro or solar. The AC electrical grids are composed of substations connected to each other by overhead, underground, or even submarine lines.
Substations are a familiar sight alongside highways and sometimes near cities. Their functions are to transform network voltages, deliver and supervise electrical flows, control the quality of electricity supplied, and protect the network in the event of an outage or damage. What do we find in a substation? Power transformers, switching devices such as circuit breakers and disconnectors to cut power in case of a problem, and measurement, protection and control devices needed to ensure safe and efficient operation. There are two types of substation: AIS, air-insulated substations, and GIS, gas-insulated substations. AIS is the most common design but requires a lot of space and overhead lines. GIS is 5 times smaller than AIS and can be indoor, which is leading to increasing usage today. To plan, operate and manage large interlinked systems, we need control centres, where operators monitor grid status. They will adjust to electrical demand variations in real time using sophisticated network management systems.
In connecting larger networks across countries or continents, we are facing a challenge. Directly connecting AC grids with different frequencies is not possible. DC is the answer. We therefore convert AC into DC to enable the interconnection. DC technology has improved spectacularly since Edison's time. Modern DC systems can transmit 5 times more megawatts across the same pylons and lines, making DC increasingly attractive to grid operators and industry. Moreover, HVDC dramatically improves power flow reliability and stability.
In the modern world, we use 20,000 million watt-hours of electricity per year. This is expected to nearly double in the next 20 years, but levels of electrical consumption vary dramatically from country to country. Each country's energy mix varies. For example, Denmark gets 20% of its electricity from wind farms, while in Poland, 94% of electricity is generated by coal-powered stations. In terms of electricity consumption, industry uses almost half of all the electricity generated, alongside residential users and then commercial and public services. Today, over 40% of our current power is generated from coal-fired plants, and only 3% comes from renewable sources. But by 2035, renewables will account for more than 16% of all power generation, as we face a scarcity of resources and the challenge of reducing CO2. Looking to the future, electrical engineers are developing new technologies and solutions needed to cope with the challenges of our changing world. Reliability and stability. Today, countries move to more sustainable generation like wind or solar, which are intermittent and unpredictable energies. Consumers are becoming proactive, acting as small power generators with solar panels on their homes or offices, and are taking control of their consumption. Grids are becoming larger, multi-directional and more complex to manage. Integrating renewable energy sources. Renewable energy sources such as wind and solar energy have less impact on the environment, but their variable nature means that integrating their output into the network is not easy. These energy resources, more and more decentralized and small scale, are often associated with demand response and energy storage and make the distribution networks more complex. Energy efficiency. At the moment, up to 16% of power generated is lost in the grid, like water from a leaking pipe. Strong efforts are being made to reduce these losses through equipment design, energy management and technologies like power electronics and high voltage direct current (HVDC) transmission. HVDC is the technology behind the trend towards supergrids that interconnect countries, regions and even continents. It's also a technology that helps connect power plants located very far from consumers. To respond to these challenges, electrical grids have to become more intelligent. The smart grid integrates power electronics along with modern information and communications technology to allow dynamic, real-time management of the grid. As a pioneer and global leader in its field, Alstom Grid is committed to meeting these challenges, helping to shape the future of our electrical grids.